Earth Systems 3209. Unit 4, the forces within Earth. References for this unit can be seen in chapters 4, 15, 16, and 19, and also in Appendix A and B of the curriculum guide. Unit 4, Topic 3.2. This topic will look at faulting and folding and deformation within rocks. We will focus on defining faulting and folding and relating these to the factors that affect deformation. We will also focus on describing the different ways faults and folds are classified. And lastly, we'll focus on using a drawing to describe the main parts of a fault and a fold. When we look at faults and folds, faulting and folding are two features seen in collision mountains. These features occur when stresses are greater than the strength of the rock, and the rock will deform. Scientists noted that when stress is applied to rocks, they first respond by deforming elastically, that is, bending. Once the elastic limit is reached, then one of two things happen, depending if the rock is in a deep earth environment or a surface environment. If the rock is in a deep earth environment, the rock will deform by plastic deformation, which result in folding or flow. If the rock is in a surface environment, plastic deformation will occur up to the elastic limit, when it will then fracture. We can see references in the text on pages 421 to 432 concerning faulting and folding. Let's look at faulting first. A fault is a break or crack in Earth's crust along which movement has occurred. Three parts of a fault include: number 1, the hanging wall. This is the top part of the rock above the fault plane. Number 2, the footwall, which is the bottom part of a rock below the fault plane. And number 3, the fault plane. This is the surface that separates the two moving pieces or blocks of rock, and generally is located between the two. If we look at the hanging wall versus footwall, the hanging wall is located above the fault plane. So the line separating the two fault blocks, traveling down at an angle, that is referred to as your fault plane, where we see the movement. The hanging wall would be located above the fault line, whereas the footwall is located below the fault line. So if we were just going to draw a fault line in any direction, like such, the hanging wall would be located on the side which is above, and the footwall would be located on the side which is below. The concept of hanging wall and footwall along a fault was first introduced when mining used to follow fault lines within rocks. In the diagram below, we see that a miner is basically in a rock tunnel, and the hanging wall is above the ore vein, and the footwall is located below the ore vein. And the ore vein generally follows a fault. And in the diagram just above here, we can see the fault that moves down to the right, where the hanging wall is located above and the footwall is located below. It's got its name from when miners used to be in the tunnels looking for minerals in the ore vein, which follows faults. They would hang their lantern on the rock above, and they would be standing below the ore vein on the rock below. So therefore, the rock that they were standing on was termed the footwall, and the rock where they used to hang their lantern above the fault plane itself, and that would be the ore body, would be called the hanging wall. And this is where the terminology hanging wall and footwall was derived. One way that we can determine hanging wall from footwall is when we look at the fault. We can draw a stick man across the fault plane, and the part where the stick man is standing would be called the footwall, and the part where his head is would be called the hanging wall. So that would occur, or would be the case, in thrust faults or reverse faults, and also in normal faults. In a normal fault, the hanging wall tends to move down, whereas in a reverse fault or thrust fault, the hanging wall will tend to move up. But again, for a normal fault, if we draw the stick man across the fault plane, he would be standing on the footwall, and the part where his head would be called the hanging wall. So this is one way that we can determine footwall from hanging wall. There are generally two types of faults. When we look at faults, faults can be classified as number 1, dip-slip faults, or number 2, strike-slip faults. The 4 different types of dip-slip fault include a normal fault, a reverse fault, a thrust fault, and a Horst and Graben. When we look at both or all 4 of these examples, we will notice that we have vertical displacement. So when we look at all 4 types of dip-slip faults, there will be some vertical displacement of the rocks. Whereas when we look at strike-slip faults, we can have one example of a strike-slip fault would be a transform fault. And transform faults can either be right lateral transform faults or left lateral transform faults. And when we look at the different types of strike-slip faults, we see no vertical movement. So there's no vertical movement along strike-slip faults, whereas when we look at dip-slip faults, we do see vertical displacement within the rocks. If we look at the different types of dip-slip faults, first let's look at the normal fault. A normal fault is caused by tension forces. And when tension forces act on rocks, the hanging wall tends to drop in relation to the footwall. Let's draw a diagram of a normal fault. When you draw a diagram of a normal fault, we can first draw the actual fault plane. And from here, we know that the hanging wall will drop down because we have tensional forces, which causes the 2 plates to move apart. The hanging wall drops down, so we can now draw in the hanging wall, which is located above the fault line, and the footwall would be located below, so we can draw that in. And we notice the hanging wall moves down in relation to the footwall. So again, just to double check your hanging wall and footwall, we can draw our stick man across the fault plane, and he would be standing on the footwall, and his head region will be on the hanging wall. And in relation to motion, we have tensional forces again, which pulls the plates apart. And we see our hanging wall moving down in relation to our footwall. When we look at a reverse fault is caused by compression forces, and compression forces causes the plates to move together. In this type of fault, we see the hanging wall, which moves upward in relation to the footwall. Let's draw a diagram of a reverse fault. So again, we can draw our fault plane, and if the hanging wall, which is located above, moves upwards in relation to the footwall, we can now draw our hanging wall. And in relation to our hanging wall, we can then draw our footwall. And in this case, the hanging wall would move upwards in relation to the footwall, and this is caused by compressional forces which move toward one another. So if we want to check, we could draw our stickman across our fault plane, and again, his head would be on the hanging wall, and his feet would be on the footwall. So this is a good way to check to see which type of fault you have, whether it be a normal fault or a reverse fault. The third type of dipslip fault is called a thrust fault. A thrust fault is caused by compressional forces, and again, if we have compressional forces, the hanging wall will move up over the footwall, but in this case it will be a low angle reverse fault, and the angle is usually less than 45 degrees. So if we refer to the diagram to the right, we see the arrows pointing towards each other, which represents stress, and the stress would be compressional forces in this case. The hanging wall would move up over the footwall, and if we want to check hanging wall versus footwall, we can again draw our stickman across the fault plane, and he would be standing on the footwall. His head region would be on the hanging wall. So a low angle reverse fault, as the one you see in the diagram here to the right, would be an example of a revert or a thrust fault, which is a low angle reverse fault. And the fourth example of a dipslip fault is what's called a Horst and Graben. A Horst and Graben is formed by tensional forces, and the Horst is the uplifted block of crust bounded by two normal faults, and the Graben is the valley formed by the downward displacement of a block of crust bounded by two normal faults. And by definition, a normal fault would have the footwall below the hanging wall, and the hanging wall would move down. So to check to see if we have normal faults, we could draw our stickman again across our fault plane, and he would be standing on the footwall, and the hanging wall is the region where he would have his head. Even on the other side, if we draw a stickman across, he would be standing on the footwall, and his head would be on the hanging wall. So in this case, a Horst would be the block of crust that is basically higher than the Graben, and it is bound by two normal faults, whereas the Graben would be a valley. That would be a valley, which again will be bound by two normal faults. So we have Horst and Graben is the fourth example of dipslip faults. If we now move and look at strike slip faults, our main type of strike slip fault is what's called a transform fault. And the transform fault is caused by shearing forces. These are forces that move past one another without any vertical displacement. In a transform fault, we generally see the two plates slide side by side in opposite directions, and we have no vertical movement. You can generally have two types of transform faults. One is called a left lateral transform fault, and the second is called a right lateral transform fault. If you look at the diagrams to the right, if you look at a geological map, this is a symbol we would generally see representing a strike slip fault or transform fault on a map. We would see an indicator such as a mid-oceanic ridge, which will be one of the popular symbols you see on geologic maps. And the ridge would be separated by two plates moving in opposite directions. And these arrows represent shearing forces along the strike slip fault, for example, a transform fault. If you look at the different types of transform faults, we generally have what's called a left lateral strike slip fault and a right lateral strike slip fault. To determine which type of fault you have, you could stand on one side of the fault and look across to the other side of the fault. Once you look across the fault plane, whatever side or whatever direction the opposite block is moving, that would be the type of fault you have. And in this first diagram, we see that the block moves to the left. Therefore, if it moves to the left, we have what's called a left lateral strike slip fault. So let's have a look at the second diagram. If we stand on the fault block on one side and we look across and look at the direction in which the block moves on the opposite side of the fault, we notice that this fault block is moving to the right. Therefore, it would be called a right lateral strike slip fault. And our fault plane would be the boundary between the two fault blocks. So here we see shearing forces moving in opposite directions, which will cause one block to move in one direction and the second block to move in the opposite direction. Look across the fault line and you see which way the actual fault block moves on the opposite side of the fault, and that would be the type of transform fault you would have. So the diagram to the right, if we look across, we notice that the fault block on the far side moves to the right. Therefore, we have a right lateral strike slip fault. So this is the way you determine the type of transform fault you have, if it's right lateral or left lateral. Let's look at some folds. When we look at folding, folding is the bending of rock layers, and folding is generally caused by compressional forces. They are slow, continual compressional forces, usually at depths, which result in ductile deformation, which we call folding. When we look at a fold generally has two parts. One part is called the anticline. That's where the crust moves upwards, forming a hill, and this is referred to as an upfold. And the second part of a fold is called a syncline. A syncline forms when the crust moves downward, forming a valley, and we generally refer to this as a downfold. So if we look at the diagrams to the right, we'll notice that in a folded layers, we tend to see what's called a downfold and an upfold part of a fold. One way that we can determine the upfold from a downfold, or an anticline from a syncline, an anticline will form an A, and the syncline will form the Y. So to determine that, if we draw a line straight through the folds, the part of the fold that makes the letter A would be termed the anticline. So A would stand for anticline. So if we do this in a drawing, we could just draw a downfold and an upfold. And if we make these layers downfold and upfold, and if we draw a line straight through, the part that makes the A would be referred to as the anticline. That's a good way we can check the C anticline from syncline. Let's look at some examples. Example number 1 reads, which results from shear forces? Shear forces are forces that move in opposite direction, and they are predominant during strike-slip faults. A strike-slip fault would be a transform fault. So our answer to this question would be D. Second question reads, which type of stress and faulting occurs at divergent plate boundaries? So we're looking for the type of stress and the type of fault that would result at a divergent boundary. When we look at divergent boundaries, we notice we have plates moving apart, diverging. Therefore, we must have tensional forces. So when we look at our answers, we see that C and D both have tensional stress. Also divergent boundaries we tend to have plates moving apart. Therefore, one, the hanging wall moved down with respect to the footwall, and this would be a normal fault. So our answer to this question would be C. We would see tensional stress and forces at a divergent boundary, and this would result in normal faults. So our answer to this question would be C. Example number 2. It says, based on the diagram, which fault is matched correctly with the corresponding stress? So if you look at the diagram to the right, we notice that the arrows are pointing toward one another, and this indicates compression forces. So if we look at our answer, we see A would have compression stress, and C would have compression stress. And compression stress would cause the hanging wall to move up over the footwall. So in this case, our answer would be C. We would have a reverse fault caused by compression forces. To check for hanging wall versus footwall, if we look at our diagram and we draw our stick man across our fault plane, his feet would be standing on the footwall, and his head would be on the hanging wall. So therefore, we notice that the hanging wall moves up with respect to the footwall. Therefore, this would be a reverse fault. So the answer again is C. Reverse faulting occurring because of compressional forces. Your turn. Take the time and complete the following question. You can pause your recording now to prepare your answer, and the answer will be on the following slide. With the aid of a clearly labeled diagram, describe the difference between a normal fault and a reverse fault. So in the question, it asks you to refer or draw with a clearly labeled diagram and describe the difference between a normal fault and a reverse fault. So those are the three things we need to include in our answer. So our solution should read as follows. A normal fault is formed when tensional forces cause movement within Earth's crust. The hanging wall moves down with respect to the footwall. So those 2 points would describe what a normal fault is. And if we look to the right, we would see a diagram which represents a normal fault. We see the hanging wall, which is the part of the fault located above the fault plane. Again, we draw our stick man. He will be standing on the footwall, and therefore the hanging wall moves down with respect to the footwall, and this is caused by tensional forces, which are indicated by the blue arrows moving apart. So these 2 points in the diagram would describe a normal fault and what a normal fault would look like. When we look at a reverse fault in comparison, a reverse fault is formed when compressional forces cause movement within Earth's crust and the hanging wall moves up in relation to the footwall. So if you look at the diagram to the right, we'll notice that the hanging wall moves upward in relation to the footwall. So again, to double check our hanging wall and footwall, draw a stick man across your fault line, and his feet would be on the footwall. When we look at a reverse fault, we have compression forces indicated by the blue arrows below, which move toward one another, and this would indicate why one block, the hanging wall, would move up over the footwall because of the compressional forces. So these are the main points that you would include when comparing a normal fault with a reverse fault. In summary, let's look at the overview of the points covered in this presentation. A fault is a break or crack in Earth's crust along which movement has occurred. And when we look at a fault, there are generally 3 parts to a fault. The different parts would be the hanging wall, which is located above the fault plane, the footwall, which is located below the fault plane, and the fault plane itself is the line at which we see vertical movement in dip-slip faults. Second, when we looked at dip-slip faults, they include normal fault, where the hang wall moves down, a reversed and thrust fault, where the hang wall would move up over the footwall, and a Horst and Graben, which are structures which form hills and valleys, which are bounded by two normal faults. And the third point that we looked at under faulting would be strike-slip faults. An example of a strike-slip fault would be a transform fault. And here we have two different types of transform faults. We have a right lateral and a left lateral transform fault. Again, if you stand on one fault block and look across the fault plane, whatever direction the fault block moves on the opposite side, that would be the type of fault, strike-slip fault, you would have. So if your fault block moved to the left, you would have a left lateral strike-slip fault. If the fault block moved to the right, you would have a right lateral strike-slip fault. And the second point we focused on was folds. A fold is bending in rock layers, and when we looked at a fold, we see two parts to a fold, an anticline and a syncline. And as a review, when we look at an anticline and a syncline, if you draw a line through the actual folds, the part of the fold that forms an A would be called an anticline. So these are the main points that were covered in this presentation.